Welcome, everybody, and thank you for joining us for today's C2 Smart webinar. I'm Lizzie, the Research Project Manager at C2 Smart, a US DOT Tier 1 University Transportation Research Center. Today, we're joined by Ricardo Negri, who will present developing a framework to optimize Floodnet sensor deployments around New York City for equitable and impact-based hyperlocal street-level flood monitoring and data collection. Ricardo is a PhD candidate in urban systems in the Civil and Urban Engineering Department at NYU. And he has working experience in structural design and facility management in Italy and in the US. He also has a master's degree in applied urban science and informatics from NYU CUSP, as well as a master's and bachelor's degree in civil engineering and a specialization in structural engineering. And his research interests involve evaluating the socioeconomic impacts of natural hazards on urban communities, including floods in New York City, and investigating strategies to mitigate infrastructure vulnerabilities. And as always, we will be recording this webinar and uploading it to our YouTube channel. And please ask questions today throughout the presentation by pressing the Q&A button at the bottom of the Zoom window, and then we will read out your questions at the end of the presentation. And with that, I will hand things over to Ricardo to get us started.
Okay, thank you, Elizabeth. So today I'll be presenting the culmination of my first research project as a PhD candidate, which I carried out with Professor Luis Seferino as part of the Disaster Risk Analysis Lab here at NYU. And the project is, the long title is Developing a Framework that optimize Floodnet sensors deployments around New York City for equitable and impact-based hyperlocal street-level flood monitoring and data collection. So I'm going to break down this title throughout my presentation. So first of all, of course, today I'll be talking about flooding. This will be the main topic of the discussion. And we all know that New York has a high risk of flooding. Not just because it's exposed, not just because it's a large coastal city, but also because it's very highly densely populated, and also it hosts a complex and interconnected infrastructure. So any natural event, any natural disaster, and specific flooding has a very high impact on the city because everything is interconnected, and any area of the city that is going to be affected is going to impact a large number of people. The slides that the images that you can see in this slide are just a few of the major flooding that happened throughout the past 30 years. There is one first point that I want to make. Although those are all floods that happen in New York, they are not all generated by the same phenomenon. So what I mean by that is that there are different types of flooding, and specifically New York is exposed to three main types of flooding. Two of them, as you can see on the left side of the screen, are usually triggered by hurricane. So we know New York is a coastal city again, so it's affected by hurricanes that originated in the Atlantic Ocean. And one form of flooding that can happen, as is it the case of Hurricane Katrina in 2012, I think. Sorry, Hurricane Sandy in 2012. In 2012, when you have a hurricane, strong wind generated by the hurricane is going to push the water into the city, and this is one type of flood. The other type of flood that affect New York is pluvial flooding. So when there is intense raining, again coming from a hurricane possibly, the sewer system is not capable of managing that amount of water. On the other side, there is another type of flooding that is often overlooked, which is tidal flooding. So high tide can generate flooding also in inland parts of the city because of the backup from the sewer system again. And this type of flooding is not as destructive as the other two, but has a much higher frequency. So all those types of flooding with different intensities and frequency are all affecting and impacting different communities in the city. One other point that is important to make is that among those three types of flooding, pluvial flooding has become more of a threat in recent years. In fact, in 2021, it was the first time in which intense raining was brought by the remnants of Hurricane Ida caused a high number of fatalities. 13 people lost their life in New York City only, directly because of the flooding that resulted. And also it caused hundreds of millions of damages towards the city. So as New York is so exposed to flooding, of course, there are several initiatives aimed at improving resilience and providing mitigation. We can look at those initiatives to understand what are the needs of the city in terms of mitigation and resiliency. So, for example, we have the Build It Back program. Is one of the needs is, of course, to provide money to retrofit the buildings of the city. Other initiatives are the construction of defensive infrastructure, such as the East Side Coastal Resiliency Project, which is building a levee to protect the East Side from a storm surge. Other initiatives that are also well known are the implementation of the drainage system throughout the Green Infrastructure Plan by DEP. There is another need, although that is also fundamental and instrumental to all the others, which is data collection. So data collection is important for several reasons. One, of course, is to provide afterwards information after a flood event to understand which areas, how different areas were affected. There are several methods to do that, for example, through remote sensing or the traditional gauges that are deployed in some specific areas. But if we can do data collection in real time, then data can also serve during the emergency itself to, for example, coordinate emergency efforts. And here is where the Floodnet projects came in. So the Floodnet project is a consortium of research institutions, city agencies, and activists that is trying to develop a framework of networks that can provide real-time data about when there is a flood. So I'm going to explain it a little bit better in my next slide. So as you can see, the Floodnet has several sensors that have been installed throughout the city, and the goal is to expand these sensors. So this is ongoing. Those sensors consist of ultrasonic sensor that can measure the distance between the ground and the sensor itself. So whenever there is a water level increasing, they basically can, by difference, they can record the depth of the flood. And in this graph here, you can see the data that we're recording during Hurricane Ida in 2021. And you see two peaks. The second one corresponds to Hurricane Ida, which happened at the end of August. And a few weeks ago, there was another hurricane which also triggered flooding, and that was Hurricane Harry. So you can see this was to give a quick explanation of, in a few words, of how the Floodnet project works. Now I come to our collaboration with the Floodnet project. As I said, the current number of sensors that are deployed is somewhere between 30 and 40 sensors out there, and their goal is to deploy 500 sensors in the next 3 years. So that means that a lot of sensors have to be deployed, and we have to decide where to deploy them. There are more than 500 possible locations. There are several places that are subjected to floods. So we need to decide a prioritization strategy. And our lab was was tasked with developing this prioritization. This is a brief explanation of how the traditional design of a network sensor is carried out. usually you already have a sensor taking measures, and the traditional approach is look at the information that those sensors can provide. So it's based on information theory. You already have several sensors in the field, and then you decide how to optimize this network by selecting only those sensors that provide meaningful information. Of course, this is not our case because we're starting from we don't have sensor measuring out there, so we cannot use their information to decide which are valuable and which have to be discarded. Instead, we need to start from scratch. So we choose a different approach, which is we decided to adopt a stakeholder-centric approach, which basically consists in grouping together all the people that can benefit from those data, from the data of the sensors, and try to understand which use they would do of those data, and based on their needs, then decide where to deploy those sensors. The first step was to host a workshop in which we hosted around 40 participants from city agencies, research institutions. There were professors from NYU, but also other universities, and the private sector, mainly insurers. And we structure our workshop into 3 questions. The first one was how all the participants would use those sensors, and there was a group discussion. So first, people were given some time to think about themselves, how they would use the sensors, and then everyone had the opportunity to share their point of view. The second part, the second group of questions was to provide some metrics that each person would use to decide where to place those sensors. And we asked them to think in 2 ways. One was base those metrics on their own needs. So based on their own scope, for example, the people from the emergency management or the people from the insurance, how they decide, how they scout the locations to deploy their sensors, and then do the same exercise, but this time keeping equity in mind. So how would you deploy those sensors with an equity perspective? So to benefit not just themselves, but also communities that are not represented at the workshop. So typically underrepresented communities. And following this, we shortlisted a set of metrics, and we practiced this analytical hierarchical process to assign a weight to each metric. And the outcome, of course, was again a set of metrics so that we could objectively compare different locations across New York City, and eventually have a ranking of locations for our prioritization. This is just a quick slide about how the analytical hierarchical process works for those who never encountered it. It's just a technique for establishing priorities. So you have a few alternatives. In our case, were the metrics that were selected in the first part of the workshop. And then you do a pairwise comparison in which you compare each metric against the other. After all the participants assigned their importance factors, we collect the data and we put them in a matrix, and eventually the outcome is, as you can see in step number 4, each alternative receive an importance weight. Those are the final metrics that were selected. As you can see here, there are 2 different sets of metrics. The 8s on the left represent the stakeholder needs, so it was question number 2. And the one on the right, they represent the metrics that were conceived while thinking about equity. I listed them here separately because you will see like how we will manipulate those metrics and combine them. It's important that we have clear this distinction between the stakeholder needs metrics and the equity metrics. Here I'm going to show briefly how our method works. So for each metric, in this case, I'm plotting the subway stations, which was one of the stakeholder metrics. So we use the GIS system to spatially plot those stations. And then we overlap this data with the flood maps. So we select only those stations that are within flood-prone areas. The third step is to divide the city into geographic units. So here, for example, we're using census tracts, and then after we divide the city into geographic units, each geographic units which we can count the number of stations that are within each unit. And eventually this gives us a way to compare different geographic units, because if one area is hosting a large number of stations, then it receives a higher priority versus another area in which there are no stations or fewer stations, which receives a lower score. After repeating this process for all the metrics, then we need to combine those metrics into a final index. The first step was to normalize each metrics, because when we calculate the metrics individually, each one is on a different scale. So it would not make sense to combine them just as they are. We needed to normalize them first. And we did so using two alternative methods that eventually will be compared, and we will select the best. So the first method was to divide each metric by its maximum value. So we're scaling everything between 0 and 1. And the other method was to divide it by the mean value of that matrix plus one standard deviation. This is similar to the z-score for those of you who have encountered that before. It's just the z-score usually has both positive and negative values. So we wanted to keep everything positive, so from 0 and greater. So we use this normalization, the mean value plus one standard deviation. After we normalize all the metrics, then we have to combine them. The combination happens in two steps. So you remember first we have two separate sets of metrics, the stakeholder metrics, which we called M, and the equity metrics. Each set has 8 metrics. So the first step is a combination of those metrics separately for each set. And for this, we use the weights that we defined with the analytical hierarchical process. So the first step is just a linear combination where the weights of each metric are the weights established in the analytical hierarchical process. And this first step leads to two combined metrics. One, the combination of the 8 stakeholder metrics, and the other one, E, is the combination of the 8 equity metrics. Then there is step 2, because we need to combine those two combined metrics into a final one. And for this combination, again, we tested two methods, a linear combination and a geometric combination. And again, afterwards, I will show you how we selected the best combination. So again, reiterating on what I just said, we used two normalization techniques and two combination techniques, which leads to having 4 different final combined indexes. As you can see, I'm listing here the formula for the combination. It can be either linear or geometric, and there are those coefficient alpha and beta. I'm just explaining briefly how we selected those coefficients. Those coefficients were selected based on the constraint that the correlation coefficient between the final metric and each one of the two metrics should carry the same correlation coefficient. So this is just like a technical detail. And this is the outcome of our comparison. So this step here is a little bit tricky. So I'm happy to go over it again during the Q&A question. I'll just try my best to give an overview of what we did. So you see in each graph, so let's look at the stakeholder, for example, the one on the left. We have 4 lines. Each line corresponds to a normalization plus combination method. So now we are comparing the different combination and normalization method that we use to calculate our final metric. On the x-axis of this graph, you see the number of prioritized areas. Let's say, for example, we want to deploy 500 sensors. On the y-axis, we calculate how much of the metrics we are capturing with those 500 sensors deployed. Of course, we want, for a given number of deployed sensors, we want to have the maximum possible we want to capture the highest possible amount of metrics because that's eventually our target. And as you can see, for both the stakeholder metrics and the equity metrics, in the range of 0-500, the best combination of normalization and combination is normalization by mean value plus sigma and the linear combination. So for our final metrics, we eventually applied those normalization and combination technique. So now we have our final metric, which is a combination of all the 16 initial metrics, and we can map our results. This is a map. This is a heat map showing the intensity of our final coefficient. As you can see, there is no scale. There is no legend because the value of the metric doesn't have any meaning by itself. It's just a relative importance. So it's what really matters is the intensity of the color of the areas on the heat map. And the 4 areas highlighted are just 4 examples that belongs to the top 10. For example, we can see Lower East Manhattan. And what's interesting is to look into those locations and see which of the metrics are driving, why they belong to the top 10 of the final combined score. So we can look at each one of them and see why their score is in the top 10. For example, in the case of the Lower East, that's specifically the region of Stuytown, which is home for, I think, about 1,000 residential units as a large project that was large public housing project that was built in the 40s, I believe. That now is no longer public housing, but you have a huge number of residential units all concentrated in a flood-prone region, and that region is prone both to storm surge and pluvial flooding, so it's very exposed. Then you have Flushing, the neighborhood of Flushing in northeast Queens. For those of you who don't know, Flushing is the terminus of the 7th line of the 7th train. So the station there has a huge annual ridership. It collects all the people living in the surrounding area, take their train from there. And it also has a high social vulnerability index. Because Flushing is home to several immigrants communities. For those of you who don't know, the social vulnerability index is an index provided by the government, the federal government, that quantifies how vulnerable are the communities in each census tract. Moving forward, we can see also another small area in Brooklyn, which is denoted with the capital C, and that's South Williamsburg. The reason why the score of South Williamsburg is so high is because there we have a large concentration of environmental remediation sites. And you can go on Google Earth, for example, and you can see the pictures. There are a lot of land pieces there which are undeveloped because the ground is contaminated with pollutants. So that was one of the metrics that we used in our that we derived in our workshop. And finally, also the other example that I'm bringing here is Springfield Gardens. Springfield Gardens stand up because it's home to electricity substations. One of the substations that direct electricity throughout the city. So it's and it's also flood prone. So that's a strategic infrastructure in case that needs to be protected in case of flooding. And also the Environmental Justice Index, which is another index similar to the SVI, this time provided by the Environmental Protection Agency, has a higher score because of the high level of pollution in that area, given especially by the high traffic that that area experiences. So I gave an overview of how our metric works. now let me go back to the Floodnet project and how they are doing their prioritization at the moment. First of all, the Floodnet project collaborates with city agencies. For example, the DEP, the DOT, and those agencies, they already have their own priority areas. They already have areas that they want to investigate. So basically, they come to the table and they say, we would like a certain amount of sensors to be deployed here and there because they have their own reasons to do that. So this is another way to guide prioritization, let's say. Also, together with the Floodnet project, again, we are also developing what we call the benchmark metric, which is a simplified metric that tries to give is not stakeholder specifically related, but try to give like a broad picture and considers residents as the center. So we define this benchmark metric as the extent of flooded area in each community times the population density times the social vulnerability index. So one might ask, so what about the metrics that we define and the final combined metrics? Well, right now, in this moment, we are using those metrics as a mean of comparison and discussion. Let me make an example. For example, if the DOT wants to has a set of locations that they want to monitor. Let's say maybe they bring to the table 50 locations. I'm just making an example, and they say, okay, we would like those areas to be monitored. One of the metric that we used was the annual average daily traffic. So among the locations that are suggested by the DOT, we can use our metric to give a prioritization of those locations. And so we can have a discussion with there can be a discussion with them to see how to prioritize their location. There is an insight they might not have. So at this stage, this is the use that we're making of the metric that we developed. The next steps of this project, of course, we started the discussion about the uses of sensors data, but this question is still open, and we hope that the number of stakeholders that can be involved in the discussion can be expanded. And so our hope is that we can come out with even more uses of the sensors and more metrics that can be included in the process. The other thing that we consider interesting is the need of a platform that the city could have that integrates the city data and the flood data and match them automatically. So right now, you all know, you're all probably familiar with the NYC open data. The city has a great extent of data, and also there are data from the federal government that are available online. But there should be a tool that can somehow incorporate those data and match them with the flood data. So this is still missing. So this is something that our team wants to investigate for our next step towards the implementation of this project. And finally, one other thing is that the more sensors get deployed, the more will be possible to analyze the data and compare them in terms of the information that they bring. So the framework that I mentioned at the beginning of the presentation, the one that is based on information theory. So when you already have a large number of sensors deployed and you want to optimize your network, this type of analysis will be possible when enough sensor will be out there, and this will be a very interesting analysis because, for example, you might see that two sensors that are spatially that are monitoring two different areas, for example, you could find correlation. So when one sensor measure flood, the other one also measure flooding. And so this is just an example to show how you can identify redundant information. And this is another step that is interesting and we plan to carry out. Before concluding the presentation, I would also like to talk briefly about some related projects that we carried out over the past 12 months, and that are somehow related. They are all related with the main project that I just presented. For example, this one, the first one I would like to start is a project that we did in the context of the undergraduate summer research programs. In both, we started last year in 2022 and we completed this year in 2023. We took 2 metrics out of the 16 that we identified in the workshop, which they are both related with the model, the flood model, the flood maps accuracy, and the reporting by the residents. So what we did in a few words is a comparison between the outcomes of the flood maps and the calls that are issued through the 311 reporting system to see if the outcomes in terms of flooding match. And again, this is an example, an excerpt of this study. You can see here, this is in Sheephead Bay, as a location that is expected to flood a lot based on the flood model, but the number of 311 calls is relatively low. So we identified those locations, and then we visited a few of them. And in this case, what we found was very interesting. For example, this is a neighborhood of houses that are a few meters below the street level. And we spoke with the residents there. And first of all, it's that specific community is a Cantonese-speaking community. So we could communicate with them just because one of our students was a Cantonese speaker. Otherwise, it would not have been possible to communicate with them. And what the information that they provide is that they experience flooding with a very high frequency, even more than what the model would predict. But they are not aware of the 311 reporting system. And even so, it would be difficult for them to use it because they can speak only Cantonese. So this type of analysis we think is very relevant because it can help the city to find location in which the reporting system, which was intended to provide resources to target areas that need resources, and basically identify location in which the reporting system is not working well. Sorry. Oh yes, these the outcomes of this study where we presented them last July in Dublin at the ICASP conference. Another project that was related was the CASP 2023 custom project. In this project, the students look at the storm surge and they analyze the 500 years floodplain. So we're talking about storm surge now. And using the depth damage curves provided by the American Corps of Engineers, they estimated the damages to residential buildings in each census tract. And then they compare the damages with the coping capabilities of the community. So in a few words, they estimated if there's a storm surge, how much would be the damage to the residential buildings for each community, and what's the ratio of those damages with for example, the median income of that community. So by calculating that ratio, you can estimate what's the coping capacity of different communities when it comes to when a flood event happens. And the outcome of this project was the implementation of a web page that is available. I'm happy to share the link after for those who are interested. And is an interactive Tableau page in which people can interrogate for each area. They can see this coping capacity score that was calculated. And finally, all the research that we carried out and what I just presented here is being summarized in a paper that will be submitted soon for peer revision. which is the title. You can see it here as prioritizing flood monitoring census area in areas in urban areas, a stakeholder-based and equity-driven approach. So now I'm to the conclusions. There are three key points that I would like to make after all this discussion. The first one is that it's based on our findings and based on the general idea that we decided to use as an approach for the prioritization, is very important to include all the stakeholders, because stakeholders can provide insights on how to use the data and eventually what matters when we decide where to locate those sensors. The other point, of course, it comes in hands, is the importance of including equity, having equity, embedding equity in this process, because by definition, when you have a set of stakeholders that take part in the decision process, you also have some stakeholders that are not represented for different reasons. And so it's always important when we make this type of decision to consider the needs also of the people that are not represented, that are not at the table. Okay, I'm gonna answer the question. Okay, and the final point that I want to make is okay, we came out with a final combined metric, but as we saw, the way that our study is being used by the Floodnet team is it requires a more flexible approach. So basically, it's good to have a final indicator, but it's also very important to have a system that is open. Let's say that you want to add more metrics, for example, or you want to change the weight that you are assigning to each metric. So it's very important to build a system that it's open and can be integrated, and you can also look at separate metrics. You can look at metrics individually for the eventually for the final prioritization, and that's it. Okay, thank you. Now I can take some questions. I've seen already two in the chat. Elizabeth, let me know, should I address those questions or
just so everybody can know what it is. And then if you have a question of your own, please enter it into the Zoom window by pressing the Q&A button at the bottom of the screen. And we have two right now, the first of which is, how do sensors communicate with emergency services in real time when it senses high flood level?
Mm-hmm. Okay, so right now the sensors, the data of the sensors are collected directly by the Floodnet team. So there is no direct communication right now with the city agencies. Although the platform is public, is available, anyone can go on the internet and see the data in real time, but there is no direct connection yet. Those data are all collected by the Floodnet team and made public on the platform, but there is no direct link yet with specific agencies. Although the data are available, and you can, if you Google, for example, Floodnet New York City, you will find their dashboard and you can access all the data.
And then the second is, what is the threshold for sensors to trigger emergency responses?
Okay, again, this has to be still to be decided, because the sensors right now are not directly used yet. So it's still experimentation going on. So there is no protocol defined so far. Probably there will be one day. I'm sure this is a very good point. They will have to decide, for example, for the emergency department, that's a specific stakeholder. When do we want to have an alarm sent out? So there will be a moment in which they will have to make this decision, but we are not at this stage at that stage yet.
Great. That is our second of two questions at the moment, but if you're typing, feel free to keep going. Otherwise, thank you everybody for joining and to Ricardo for presenting today's webinar. A recording will be available on the Center's YouTube channel and website. And as always, this webinar was brought to you by C2 Smart and the USDOT's University Transportation Center program. And we have no further questions, so we can close out. And thank you again, everybody, and have a great day.
Thank you very much.
Have a good one.